All right, good morning, 11th grade. I hope you guys are doing well this morning, that you are looking forward to your week. Even though you have to spend it at home, hopefully you have found some fun way to entertain yourself that is still productive to society. Anyway, I hope you guys have been doing well. We are going to pick up where we left off in our notes last week. Last week we talked about redox reactions, and Leo the lion says, Grr, how oxidation is a loss of electrons and reduction is a gaining of electrons, and how if something is doing the losing, there has to be something somewhere doing the gaining. And so that's what we focused on with our notes last week. Hopefully you took a look at that video that I posted Wednesday in the LMS, just to take another look at it, to familiarize yourself with it. So we're going to move forward. We're actually going to finish the chapter this week because both sections of the remaining notes are fairly short. So we're going to finish up the notes for this week. Please make sure you are getting your notes down. They are going to count for a grade in one way, shape, or form. So just keep that in mind. So, electrochemical reactions, electric current in an aqueous solution. That's what we're going to look at first. Now remember, aqueous solution has to do with water. It's not just a liquid. When we're dealing with an aqueous solution, we're dealing specifically with water. So, current is the flow of electric charge. Okay, it's pretty basic. Electric current consists of moving electrons in metals. In order for there to be a current, there has to be electrons moving somewhere. Okay, you cannot have a current if there is not electron movement. Electrochemical reactions, these are reactions that involve an electric current. So electrochemical reactions typically tend to take place in aqueous solutions. All right, any solution, and again, we're dealing with aqueous solutions here. Electric current is the result of ion movement through the solution. Now remember, ions are atoms that have gained or lost electrons respectively. All right, anions and cations. Electrolytes, these are substances that dissociate or ionize in water to produce ions that can conduct electricity. So what happens is these ions, they dissociate, they break apart from one another, and that breaking apart allows an electric current to be produced, or to be conducted, not produced. Okay, the electric current is produced from an outside source, but when the ions dissociate inside the aqueous solution, when they break apart, it allows for the conduction of electricity through that solution. The stronger the acid or base an electrolytic solution contains, the greater its ability to conduct electricity. Okay, if you have a stronger acid or a stronger base, you're dealing with more dissociated ions. Okay, the stronger the acid or base, the more dissociated ions you have. So because you have more dissociated ions, it has a greater potential to conduct that electric current. Electrolysis. Electrolysis is the process that passes an electric current through an electrolyte to cause a non-spontaneous redox reaction. So basically, electrolysis is how you use electricity to make redox reactions. All right. Oxidation occurs at the anode and reduction occurs at the cathode. Now think of a battery. Okay, we've talked about anode and cathode before, but think of a battery. If you have just a regular 2-cell battery, it has an anode and a cathode, and oxidation occurs at the anode and reduction occurs at the cathode. If you have a D-cell battery, 9-volt battery that has the 2 prongs at the top, oxidation occurs at the anode and reduction at the cathode. The anode and cathode are electrodes connected to a power source attached to an electrolyte solution. So those are the areas where you actually hook up to create the electric current from the beginning. A half reaction represents half of an overall reaction. We've talked about half reactions before, but when you are dealing with electrochemistry, you deal more with half reactions than you do full reactions, because with half reactions you look at how did oxidation occur and how did reduction occur. Okay, so you have 1/2 of each thing there for you. So a half reaction in relation to electrochemistry is more how you're going to use it, so that's why I threw the word in there for a refresher for you. The ions that complete an electrical circuit by migrating in a solution and carrying the charge are not necessarily involved in redox reactions at the electrodes, okay? So the ions that carry the electricity or the electrical current throughout the entire solution, they're not necessarily the ions that have to start the redox reaction up at the anode and cathode, okay? Just something to keep tucked away there. Electroplating. Now electroplating, sorry, let me take a drink. Electroplating is a pretty cool process, and your quiz assignment for this week has to do with electroplating. And it's a pretty cool process to watch and see done. So anyway, electroplating, this is the process in which electrolytic cells are used to form a thin coating of metal on an object, okay? Typically, things that we are common with, is that how I want to say it? Anyway, things that you are used to seeing that are electroplated. Things like silverware is electroplated. There's some jewelry that's electroplated. That's why if you wear it sometimes it starts to tarnish or it turns your skin. It's because it was electroplated. All right, but it's when you just put a thin coating of typically a silver metal, but it can be a copper metal as well, over an object to help give it a little bit more strength, to help give it some protection, and in most cases just don't make it look nice. But metals that are weaker reducing agents than hydrogen are often used in electroplating. And then a source of direct current, DC, must be used to pump the electrons through the circuit that is created in order to complete the process of electroplating. So there has to be a source of direct, there has to be a source of direct contact. There has to be something that is directly affecting the liquid that is doing the electroplating process, all right? And then voltaic cells. Voltaic cells, the best thing I can think of when I think of a voltaic cell is a battery. Okay, any type of battery. Well, not any type of battery. Larger types of batteries, okay, like car batteries. Perfect example of a voltaic cell. But spontaneous redox reactions have the ability to produce an electric current, okay? So it is possible for a redox reaction if it has enough energy behind it, if it has a strong enough acid or a strong enough base behind it, it is possible for it to produce an electric current. Voltaic cells, these are devices that convert that chemical potential energy of spontaneous redox chemical reactions into electrical energy. So what that means is a voltaic cell has all of the components inside of it necessary for a spontaneous redox reaction to occur. But it doesn't happen until you apply the power source somewhere, okay? Like with car, turning on the engine, okay? Or with batteries, sticking them into the object to actually fire it up. So constructing a voltaic cell, we were going to do this in person. We're not going to do it now because, well, the circumstances are not going to allow us to do it now. So here's just some information, I guess, since we're not going to do it, but some information that you need to be familiar with for when it comes finals time, all right? So constructing a voltaic cell, the first thing you need to look at is the activity series. Now the activity series is a listing of metals by their relative ease of oxidation. How easily are they oxidized? How easily do they give up those electrons, okay? You can find this list in your textbook shortly after section 3 of chapter 16 begins. I can't remember what page exactly. But this activity series may be used to predict the reactions of metals with each other, okay? Because of how easily certain metals lose electrons, we can look at them and say, okay, this metal is going to react very easily because it gives up electrons easily. Or this one's going to react easily because it accepts electrons easily. Metals at the top of the series are strong reducing agents and are considered active metals. And then when two different metals are involved in a redox reaction, the metal higher in the activity series will be oxidized and give up electrons, reducing the cation of the less active metal. And then a salt bridge. When building a voltaic cell, you typically have to have some sort of connector bridge, and the connector bridge is a salt bridge. All right, this is a tube that's filled with a non-reactive electrolyte. This works to divide and equalize the charges on each half of the voltaic cell and prolong its life. Now, I want you guys to do a little bit of reading, so I tucked this note in here for you, okay? Please read pages 278 and 279 in your textbook to see the breakdown of voltaic cell construction, okay? You can read about how it's done, and you can see pictures of how it's done and how the process actually works through. So please, please, please look at these pages, okay? See what we would have got to do if life had allowed us, all right? Measuring electrode potentials. The more active a substance, the stronger the negative charge that develops when the substance is at equilibrium with an electrolyte solution. So, standard electrode potential. This is the tendency of a substance to form a stronger or weaker charge when placed in an electrolyte, okay? So standard electrode potential looks at, is it going to create a strong charge or a weak charge when I plop it inside an electrolyte solution, okay? Hydrogen is relatively measured and given a standard electrode potential of 0 volt. Hydrogen is typically, if you've noticed, we've referred to it a couple times throughout this chapter, hydrogen is typically your base element, okay? It's what everything else revolves around, okay? As far as looking at electrode potential, as far as looking at electricity potential goes, most of the time you're going to deal with hydrogen first. So hydrogen in the electrode potential range, that's your base number, that's 0 there for you. Electrode materials that are more active than hydrogen have a negative standard electrode potential, and materials that are less active have a positive standard electrode potential, okay? Negative, let's see, how did I want to say this here? The reason materials that are more active are negative is because they have more free electrons, okay? And remember, the more free electrons you have in something, the stronger the negative charge of that object, okay? So put 2 and 2 together here, guys. And then obviously materials that are less active, they have less free electrons, so they have a positive standard electrode potential. Standard electrode potential is measured by a special voltaic cell containing a hydrogen electrode on one side, which is known as the standard hydrogen electrode, or She, and an electrode of the substance to be tested on the other side. And then electrode potentials are also known as standard reduction potentials because it has to do with the gaining of electrons, and reduction has to do with the gaining of those electrons. All right, last one, well not last, no, there's one more about this, but last section. Signs of the cathode and the anode. Now the anode, just some thoughts about it here. Oxidation occurs at the anode, so the loss of electrons is occurring at the anode. The anode emits electrons to the external current. The anode of an electrolytic cell is positive, but the anode of a voltaic cell is negative. This is because electrons, not electrodes. Electrons are willingly lost in a voltaic cell and forcibly lost in an electrolytic cell. So an electrolytic cell has to be made to give them up, versus a voltaic cell, it just, I don't want them anymore, take them. And then the cathode. Reduction occurs at the cathode, so this is where electrons are being gained. Okay, they're being gained in the cathode. Too many O's, I'm getting my words all mixed up. And the cathode receives electrons from the external circuit. So it receives those electrons from the anode that has given them up. Okay, it's given them up into that external circuit, and then the cathode takes them out of that external circuit. All right, so that is it for this chapter, guys. Again, please make sure that you got these notes down, that you're familiar with them, because if anything, you're going to see some of this stuff again on your final exam. Yeah, so I miss you guys. I'm praying for you. I hope to see you soon. Bye.